To understand the fine structure of the hydrogen atom, we have to follow the math. We need to construct a rigorous, step-by-step mathematical derivation of exactly what is happening inside the atom. The formal structure for this derivation relies directly on the principles laid out in David Griffith's Introduction to Quantum Mechanics. This is the standard Bohr Hamiltonian. It models hydrogen using only classical kinetic energy and the Coulomb potential energy pulling toward the nucleus. Under this model, allowed energy levels depend entirely on a single integer, the principal quantum number, n. But high-precision spectroscopy reveals a discrepancy. When we measure the actual spectrum of hydrogen, the predicted single energy levels are actually shifted, and in many cases split into multiple distinct lines. To correct the Bohr model, we have to layer two distinct physical phenomena back into our equations: special relativity and spin-orbit coupling. True quantum accuracy requires us to abandon simple approximations and mathematically integrate these complex physical realities. The first missing reality is velocity. The electron in a hydrogen atom moves at a significant fraction of the speed of light, making the classical kinetic energy approximation insufficient. We must replace the classical momentum term with the exact relativistic kinetic energy formula. Expanding the exact relativistic formula via a Taylor series reveals the familiar classical term, followed by a new small perturbation term. To understand the scale of this perturbation, physicists look at the fine structure constant, alpha, which roughly represents the ratio of the electron's velocity to the speed of light. This first-order relativistic correction is proportional to alpha squared. It is a tiny fraction of the total energy. While this mathematical correction shifts the allowed energy level slightly downward, it applies uniformly to a given state. It does not explain why the spectral lines physically split into separate bands. Relativity only corrects the overall scale of the energy. To explain the broken degeneracy, we must look for a new internal atomic interaction. The second physical mechanism is spin-orbit coupling. In our standard reference frame, we picture a heavy, stationary nucleus with a single electron orbiting around it. But if we shift our perspective to the rest frame of the orbiting electron, the system looks inverted. From the electron's point of view, the massive positive proton is orbiting it. This moving positive charge acts as a loop of current, which creates a magnetic field at the electron's position. Simultaneously, the electron possesses an intrinsic quantum spin. Because it is a charged particle with spin, it generates its own natural magnetic dipole moment. The spin-orbit interaction is simply the potential energy of the electron's magnetic moment trying to align itself with the magnetic field created by the orbiting proton. Translating this physical interaction into our spin-orbit Hamiltonian yields this equation. Notice the critical factor at the end. It is proportional to the dot product of the orbital angular momentum and the spin angular momentum. The atom's internal magnetic environment forces a coupling between the electron's spin and its orbit, compelling the energy states to split based on their alignment. The problem here is commutation. This new Hamiltonian does not commute with the individual operators for orbital or spin angular momentum. Because they do not commute, the traditional z-component quantum numbers we rely on are now useless for our perturbation theory. To solve this, we define a new operator, the total angular momentum vector, J. By squaring the J vector, we initiate an algebraic breakdown to isolate that problematic dot product. Rearranging the equation gives us the dot product expressed strictly in terms of J squared, L squared, and S squared. This specific arrangement commutes perfectly. We have found our new viable quantum numbers, shifting our basis to L, S, J, and Mj. Applying these operators to their states pulls out the scalar eigenvalues, executing the final step of the perturbation theory. By adopting the total angular momentum basis, we are able to successfully quantify the spin-orbit energy shift. We now place the fully evaluated spin-orbit energy correction side by side with the relativistic correction we derived earlier. Both corrections share the exact same mathematical order of magnitude, despite describing entirely different physical phenomena. Because they scale identically, they can be directly added together. Disaddition forms the unified energy level equation for the hydrogen atom, incorporating both relativistic and spin-orbit corrections into a single framework. These corrections for relativistic mass increase and magnetic coupling converge into one final expression for the hydrogen energy levels. Looking at the isolated spin-orbit equation, a mathematical paradox often catches students off guard: an apparent division by zero when the orbital quantum number L equals 0. But when L is 0, the numerator evaluates to 0 as well. Physically, an electron with no orbital angular momentum experiences zero spin-orbit coupling. The interaction ceases to exist. Ultimately, fine structure permanently breaks the degeneracy in L. For any given principal energy level, electrons with different L values will now measure at slightly different energies. However, because the grand formula relies entirely on J, the energy degeneracy for states with the same J value remains perfectly preserved. This exact algebraic result is completely verified by modern physics. Our perturbation derivation matches the exact analytical solution of the relativistic Dirac equation up to the fourth order of alpha. By forcing the electron to obey the constraints of special relativity and mapping its internal magnetic environment, we correct the Bohr approximation and reveal the exact mechanics driving the atomic spectrum.